Hi, everyone. Welcome to this VIS Short Papers session. My name is Chris Bryan. I'm the session chair. This session is entitled System Design. So we've got about 8 or 9 presentations for you in this session. So we will go ahead and start right now and start going through them. Our first presentation is our speaker is Tim Gerrits, and he'll be presenting Dave, a curated database of visualization examples.
Yeah, let me quickly put that on the video mode so that it runs smoothly in a moment. Optimize, yeah, should be fine. All right. Yeah, hello everyone. Thanks for the kind introduction. My name is Tim Gerrits, and on behalf of my co-authors Jens Koenen, Marvin, Petersen, and Christoph, Garth, I'm very happy to get the chance to introduce Dave to you. And I hope that after this presentation, you'll also consider yourself a friend of Dave. But we'll see about that. So what is this all about? We are part of a large national research project in Germany called NHR. And its goal is to make using high performance computing easier for all researchers in Germany, which is quite a daunting task. Yet it provides a very convenient situation for us because it means we work very closely with experts from several areas who use high performance computing in their research. We work with users who develop fluid simulations, simulate combustion, or even biomedical processes. And our job is to help them use visualization for that. But quite early into the project, we noticed something. We realized that the visualizations most groups were using in their work to analyze their data often looked quite similar to this. So quite simple visualizations, line plots, scatter plots, maybe a 2D slice of data here and there. But that's not what we expected from scientists working with inherently spatial data, right? So physical data. But when we talked to them, they all told us they really wanted to use more advanced visualization. They wanted to get sophisticated 3D views, maybe even immersive tools and visual analysis methods to really understand their data. However, they were lacking resources to introduce that into their work. And what I mean by resources is they do not have the time to learn what visualizations are out there, how techniques are called, and they definitely do not have time to learn new visualization libraries and then try to get them into their simulation code that might have been written decades ago, maybe even in Fortran, And these users often have to make sure that things are portable. So they need to run their code on their laptops for quick testing, but also work on large clusters with potentially massive data, which is another big challenge. And all of this while trying to develop new models in their own respective specific domain, right? And so I can totally understand that you would rather rely on a simple 2D plot from a Python library instead of digging into all of these aspects. So we decided to tackle this issue by creating a system that had to fulfill 3 requirements. It should help non-visualization experts to find suitable visualization techniques for their data without previous VIS knowledge. Then it should make it as easy as possible to actually use these techniques and bring them into their workflow without having to learn a bunch of new tools, but use the ones that they are already familiar with. And finally, we wanted the system to be able to grow and stay up to date. And you'll see what I mean by that. So this is where Dave comes in. Dave is a curated database of visualization examples. And I think the best way to understand what Dave does is by seeing Dave in action. So this is what Dave looks like if you access Dave, which you could do right now. Dave is actually online. You can just access it from your phone or from your computer. It's a modern, simple web interface. And while you could find a lot of additional information on here as well, the main focus lies in one central task, which is describing your data. And once you go up there and start this, Dave will try to support you by giving you suitable text that might fit your search terms or already list examples that sound like they could fit your data. And once you're satisfied, Dave will bring you to the gallery view, where you can see all the examples that are currently added to Dave that fit the terms that you added. And we could continue, remove tags, use filters, create new ones, or just get inspired by the examples that look good for your data. So when you click on something that you find interesting, you get to the page that describes the example in more detail and describes what visualization technique has been used. You see images. You can try out an interactive preview right in the browser. So you can learn more details, what exactly is shown, how it can be recreated, as well as further references. For example, where the data is from, how you can get it, papers that describe the technique itself. So a lot of information. And this is how we tackled the first issue, right? And to make it as simple as possible for people to directly try out a technique, Dave provides containerized versions of the example. So containers are the de facto standard solution in high-performance computing development because they make sure that everything is packed nicely in one place and all dependencies are working and things will run no matter if it's on a personal laptop or a large compute cluster. So in Dave, you can customize your own containers. You can choose which data to use. For example, use data from the example itself or use your own data, which container technology you prefer, and how you want to run your example, for example, using Slurm or something like that. So it just suits the workflow that the users are used to anyways. And at the end of this process, what you'll get is a simple script that then does the work for you. It downloads required files and actually runs the technique. And here too, we made sure to build upon technology that makes it easy to understand what is happening. Our current examples are based on running pair-review scripts written in Python with comments describing the code and available variables that can be changed such that you can adapt it to your own needs and know where to start. So you could, in theory, also load this trace file into pair-review and start exploring the visualization from there. So that's what Dave provides for users. But we know that this system only makes sense if it is actively used and maintained by the community. We therefore provide detailed descriptions on the website as well as template markdown files, which makes writing a new entry straightforward. And because Dave uses simple file structures, adding a new technique can be done by simply adding files using a merge request on the project GitHub. And when we showed this to collaborators, one group actually decided to fork the project code and use it as their own private place to store examples, scripts, and personal notes, stuff that would otherwise be scattered on hundreds of dead internal wiki pages. And this was a feature we didn't even have in mind when we created Dave. So to quickly summarize, we built Dave as a tool to help non-visualization experts to easily find visualization examples, especially HPC users. By using containerized code, we allow them to run, but also customize and adapt the examples on a variety of hardware, which also offers them a starting point if they want to learn more about the process. But we also realized that Dave has the potential to become a resource for visualization users as well. It provides a platform to bring approaches directly to the users who are supposed to apply them in real-world scenarios and problems anyways, right? And I think that's a real chance to bring or to bridge the gap between this research and users. But as you can see, Dave is still quite young, and there are a couple of things that we are planning. Of course, Dave still needs to grow, and we are actively reaching out on conferences and workshops to get feedback on missing techniques, features that might be helpful, and also get people like you to add their own interesting visualization examples to the database. We're also experimenting with more wizard-like approaches or machine learning-based recommendation systems. And finally, we would really like to create an API that would allow other programs to receive recommendations and examples directly from Dave. And with this, I hope you learned something about Dave and you can recommend it now and try it out yourself and maybe send us feedback, features that are missing, and especially fill it with your own examples. And with that, I'm open to any questions.
Thanks, Tim. There are two quick questions in Slido that I think we can ask. The first one is, are there any plans to support things beyond peer review, like BTK, E3, WebGL?
Yeah, so that's a question that we heard from several people, and definitely yes. So it's up to the community to decide what we do, as long as we try to follow those straightforward steps, right? Try to make it as simple as possible to use it without getting a lot of stuff in there. But this should be definitely doable, right? One thing that I think is important is we don't want to replace things like D3, right? We are trying to especially talk to people that work with HPC related data or with data that is inherently three-dimensional. So it's a little bit of a different context, which also makes visualization a little bit harder in some cases. Yeah.
Okay, great. So in the interest of not falling behind on our first presentation, there's a couple more questions on Slido. I'm going to suggest we take those to the Discord and we can put that.
All right.
Okay.
Thanks.
All right, let's go to our next presentation. And our speaker will be Venkatesh Sivaraman, and he will be presenting Counterpoint, orchestrating large-scale custom animated visualizations.
All right, great. Hi, I'm Venkat. I'm a PhD student at Carnegie Mellon, and I'm excited to share this work, Counterpoint, which is a toolkit that's open source for orchestrating large-scale custom animated visualizations. And I built this together with other folks at CMU, Frank, Dominik, and Adam. So there's a ton of great Viz toolkits out there, which I'm sure many of us have used, probably to make a lot of the tools that we're seeing at this conference, D3, Observable Plot, Vega Lite, and many others. And it's easier than ever to create beautiful custom visualizations on the web with these tools. But even having these tools, it's hard to push the boundaries in terms of animation, scale, and accessibility. So for example, in our past work in Blaze, it was hard with existing frameworks to be able to animate smoothly between two scatter plots that had tens of thousands of points each. And tools like AttentionViz and Network Analyst have these bespoke requirements for design and animation that have to be purpose-built for each project. And so through building projects like this, we noticed some common challenges that we wanted to address and build a toolkit for. So to illustrate the challenges, let's take a simpler example, a bar chart race, but an interactive version. So you may have seen charts like this on YouTube. They're pretty fun. In this interactive version, you can step through the years with this text box and see how the bars change in width and ordering. And you also see bars enter and leave at each step. And you can also step through faster and the animations would keep up smoothly, or we could even go backwards in time or skip years if you wanted. So just an overview of the different types of interactions that you might add in this sort of simple visualization. And there's several challenges that might already come up implementing this chart. So first, how do we keep the animation smooth if we want to add more visual elements or data points? If we want to make this chart scalable, we might start with SVG, which D3 works great for, but there's less support for more scalable rendering technologies like Canvas or WebGL. So if we want to switch the rendering framework later, we might need to re-implement the entire chart, which isn't great. How do we handle canceling animations or overlapping multiple animations with different properties of the same bar? That's going to take a lot of boilerplate code that we probably don't want to spend time writing. Another challenge is adding and removing bars. Well, again, while accounting for the animations entering and exiting. In Canvas and WebGL, we need to be able to keep track of which bars to render at every frame. And that gets complicated in the way we write our code. And finally, if we do use a scalable web graphics framework, it becomes a lot harder to accommodate users with different preferences about how to view and interact with charts. So Canvas elements are basically rasterized images, so they can't be accessed with a screen reader. And there's all these different preferences and alternative interaction modes we might want to support. But if our code is already so complicated from supporting Canvas rendering, we might not have the resources to support accessibility as well. So we argue that a lot of these problems can be solved by addressing just one aspect of developing these visualizations, and that is state management. You might be familiar with this term from frameworks like React, Vue, and Svelte. And what we propose is nothing too fancy, just applying similar ideas, but tailored specifically for animated visualizations. So we can create reactive components for individual visual marks that can animate independently. And then to allow for adding and removing bars, we propose separating the specified state of the plot, which is which bars are supposed to be on the screen, from the momentary state, which is which bars are actually on the screen. So some might be entering or leaving, and those are separate from the specified state. And finally, because our state management and rendering code will be decoupled, it's a lot easier to accommodate users with different preferences and needs. So we thought about how these affordances could help us organize our code and make it easier to make animated visualizations. And Counterpoint is a TypeScript framework that makes this possible. So now I'll give you a quick demo in terms of the code of how you could implement an animated chart. So let's go back to this bar chart race and see how we could write it with Counterpoint. So we define marks, which are any kind of visual element made up of several animatable attributes. And so in this little JavaScript snippet here, each mark will be a bar that represents one of the programming languages in our bar chart race. and it has these properties y, width, and alpha. So y and alpha are static values that we update manually, and width is reactive, so it can change automatically anytime we re-render the chart. So pretty straightforward so far. And now to actually render the chart, Counterpoint isn't opinionated about that. So you can use SVG, Canvas, or WebGL to perform the rendering. It's up to you. And here we use a canvas-based drawing function. Now to help us manage a potentially large collection of marks, like in these huge scatter plots or bubble charts, we can use a mark render group class. And so the nice bonus of this render group is that we can use a concept we call staging to animate the entry and exit of marks. So we specify functions that run when we need to enter and exit each mark. So here we animate the alpha of the mark from 0 to 1 and then back to 0 when it leaves. And under the hood, this actually decouples which marks are in the render group from which marks are on the stage. So we don't actually have to think about the fact that marks might be entering or leaving in the rest of our code. And so we can see that in this code that runs when you update the selected year. So ordinarily, we'd have to check for and handle every bar that's entering and exiting every time we want to change the state. It can get really complicated. But here, we just simply add the marks that should be on the screen and remove the ones that shouldn't. It's also much easier to change the animation style later on since we've decoupled the state of the chart from how we render and animate it. So we conducted a small evaluation to see what kind of overhead Counterpoint adds to visualizations. To do that, we implemented the same exact visualization in 3 major graphics frameworks, SVG, Canvas, and WebGL. And we used D3 and D3 plus Counterpoint. And here we can see, as expected, for just the D3 versions, the latency is highest for SVG, then for Canvas, and the fastest is Regal, which is WebGL based. But when we add the Counterpoint versions, we see that it's roughly equal in performance to D3 along all of the different rendering styles, and even faster in some cases. And it's also worth noting it was much easier to rewrite these implementations for different rendering frameworks using Counterpoint. So D3 offers a ton of great tools like scales, layout algorithms, and helper functions, which Counterpoint doesn't address. So it's not trying to replace that. Instead, it can be sort of an add-in that helps you manage the state of your charts, especially if you're trying to build something really big and fast. And the other benefit here is we have helpers that are that make it easier to support users' needs with accessibility. So for example, we've included the CSS media queries for contrast, color schemes, and motion as reactive attributes, so you can respond to them easily in your rendering code. And then you can also combine Counterpoint with tools like Data Navigator, which help you implement other ways to navigate charts. So for example, we implemented this Gapminder type chart in Counterpoint. You can look at this full version in our documentation. And not only can you interact with the chart using your mouse, you can also hit navigate and now use keyboard presses to navigate the chart with your keyboard and have a screen reader read a description of each data point. So despite using a scalable rendering tool like Canvas to make this animation super smooth, we were able to make the chart even more accessible than if we just use SVG. So Counterpoint is publicly available as a JavaScript package, and you can install it with NPM. There's a variety of different use cases, like scatter plots, bubble charts, bar charts, any sort of highly animated multiple interaction type visualizations that it could be used for. If you're interested in learning more, check out our documentation, which is linked here, and give us some feedback on GitHub. And yeah, I'm looking forward to taking questions and hearing your thoughts. Thanks.
Okay, great. Thanks, Venkat. So one question on Slido right now. Does Counterpoint work with frameworks that I guess that use kind of states like React?
Yeah. So several of our examples are implemented using Svelte, which is another reactive framework. You can check those out. They interplay pretty well. I mean, I guess, yeah, you wouldn't use React native concepts in your Counterpoint visualizations, but usually that's for the best because React adds a bunch of overhead. So you can kind of keep those things separate and use this as like a plain JavaScript component.
Okay, great. Okay, so I think any follow-up discussion we can take to go to Discord, and we can move on to our next speaker. That'll be Matthias Maiterth. and he will be presenting Visualizing an Exascale Data Center Digital Twin, Considerations, Challenges, and Opportunities.
I think you can hear and see me. Can you?
Yes, we can.
Okay, good. Then thank you. My name is Matthias Maiterth. I am a postdoc at Oak Ridge National Lab, and I'm going to present to you Visualizing an Exascale Data Center Digital Twin, Considerations, Challenges, and Opportunities. First, to start off with, I'm going to define what a digital twin is. That is a digital representation of historical, current, and future behavior of a physical object or process, and the goal is to optimize its performance and understand its behavior. The system that we're interested in is Frontier. That's the first exascale supercomputer with over 37,000 GPUs when it was first installed. There's a lot of infrastructure around it. We have 20 cooling towers on the building and which pump 6,000 gallons per minute. And on the bottom left, you see one cooling distribution unit supporting 3 racks, and also as an example, one of the nodes in there. So in November 2022, that achieved 1.1 exaflop, and by now we have actually added a few more racks, integrated one of the test systems in it. So in June 2024, we achieved 1.2 exaflops. And it's, as you can see, it's a massively parallel system. This project is in the context of Exadigit, where we are modeling on the one side the cooling model, and then on the other side the supercomputer with a resource allocator and power simulator, and we can feed that from telemetry, triggering these simulations, and then we want to visualize that. So here you see the overview of what we model in the cooling system, from the cooling distribution units through the different cooling loops up to the roof, and then that is modeled in Modelica. And then for the supercomputer side, we model all the power consumers, the conversions, and so on, and have a simulator that can either draw in data, and then from that compute, from the telemetry data, basically compute the total power consumption per rack, and then that is fed into the cooling model. And we can also run simulated jobs and so on. That is going to be presented at Supercomputing this year as a main track paper. But we are now looking at what about the visualization? How do you actually visualize such a thing? That's why I'm presenting considerations, challenges, and opportunities. And I'm going to present the current state of this. So the considerations. We have one system. We have 77 cabinets, originally 74. Then each of these have 8 chassis with 8 blades each. And each of the blades have 2 nodes, and then each of the nodes have 4 GPUs. So total, now this is the updated number, with 39,424 GPUs. So that's, if you put all that into, for example, I modeled that in Unreal, you have a lot of vectors, 150,000 already with only these parts in. This basically includes also memory, CPUs, cooling, the networking infrastructure. So you basically get to a lot of actors. That is a lot of component, and already simply having everything in the scene takes long, works great for a screenshot, looks good, but this is not really practical, especially not if you want to have that in an augmented reality setting. What you want in such a thing is you actually want the empty level. Then you put your 77 boxes in there, and then you interact with them as you need to look into it and want to get information. But still, this is kind of a bit of a brittle approach. If you spawn too many things in your VR headset, you actually have to have a way to back out of that to gain back performance and be able to interact with the system. And we've also added the network and basically put the Dragonfly topology in there, the central energy plant. I'm going to skip over that in this talk. And then we have the data. We want to place data onto these components, and we have a HPC telemetry platform that we rely on here. It generates 1.3 terabytes of data per day, and you really have to be careful. You're drinking from the fire hose, querying that and then deciding what you can show. So there's remote processing. Once the data gets collected, then you query that, you do local processing, and then you match the hierarchy that you have in the components within your scene to the data that you requested, and build a shadow structure, and then map one onto the other, where you skip subcomponents if no data is present in the part that you queried, and you discard the data if there's currently no subcomponent present that you spawned within your scene. And so now I recorded this from within my editor, simply loading everything in the scene, populating everything. So this is 150,000 actors streaming the data in. It's actually cool that this works. But as soon as you go to a augmented reality, AR, VR, or interactive view, that is something where you can't spawn everything. But the good thing about digital twin, in that sense where you really have everything interactive, this gives you a really good overview of the systems, even though if you load it onto a table, features may be small. So if you interact with the GPUs on the small table view, that's basically too small features to interact with. At the same time, it gives you really a good understanding of the overall system. So you can look at the central energy plant, at the system, and potentially also when having that with the anchor, multiple people looking at the same model and actually discussing about that. And then the second part is when you bring it up as a full-size system, either laying over the actual system or in an empty room. Great interactivity, you can draw out blades, look at the details, though you already have to know where in the system you are. Otherwise, it's hard to have the overview. And yeah, the overview is basically when you're already in the system, it's a large system, right? But both of them give you a really good spatial understanding where information is, and then you can, from a hand menu, trigger simulation, draw in data. Yeah. That brings us to the challenges and opportunities. As I said, we have a large-scale systems. There's always too many components to display. Even with better hardware, better headsets, we always have more data than we can display. Big data, we have a lot of data. Again, we have more than we can display. This needs to be selective, seeing what you put into your scene, what you're actually interested in, and then the combination of live or almost live data, the historic data, we can go back in a calendar view up to the first time that we had this and collecting the telemetry, and then triggering simulations or combining live, historic, and simulated data. And then for visualization, with so much data, you have to have a good understanding on how you actually present that to the viewer. So information overload, when you saw the links, that is basically too much information. How to present that, filtering, what do you actually present, and is that packages lost, or is that latency and bandwidth within specific links? So dealing with visual clutter. And then for opportunities, the digital twins are really an exciting opportunity here because each datum has a location and time, and then the value that you're actually presenting, and you don't have to stick to that layout, so you can morph it, and you're in a games engine and can really transform this. This is actually quite exciting there. And then with that, you can understand the complex system interaction, which in usual telemetry, when you have that either in a table or in other 2D views, sometimes it's hard to really understand the interaction of the systems. For level of detail, the traditional ways for level of detail are not necessarily always suitable because you want to have detail where you're interacting with. So yeah, there are potentials there when somebody goes to a detailed view and then wants to back out and see other parts. And you can always augment that with dashboards. And with that, digital twins are really an effective way to combine simulation data and 3D interactive systems. Yeah, with that, I conclude. And visit our website. We're going to present the main body of this work for the simulations at Supercomputing in November. Any questions?
Hey, great. Thanks, Matthias. I don't see any questions on Slido at this time. So how about if we have, if you have questions for Matthias, we can take them to Discord and we can follow up
So
there.
I was actually planning on having a live interactive session. I would have brought the headset with me so that we can actually, some people can test it out. If people are interested, message me on Discord and I can set up a meeting and I can basically put the headsets on and show what you actually see when you're in this. So this photo, for example, is taken from the headset. Yeah.
Great. All right. All right. Can you stop your screen share?
Oh, yeah.
We will go to our next speaker. So Yuqi Zhang will be presenting guided statistical workflows with interactive explanations and assumption checking.
Okay. Does everything go smoothly? Yeah. Okay. Okay, thanks, Chris. And hello, everyone. I'm Yuqi Zhang. I'm currently a research associate from Harvard Business School. And today I'm more than pleased to present the work that is done when I was a master's student at NYU with Adam and Will from Carnegie Mellon University. That is guided stats. It provides guided statistical workflows with interactive explanation and assumption checking, which are really important to ensure the validity. And here's the reason why. So imagine we are running a linear regression to predict housing prices. We write the code, get the result, and think we have done all of the jobs. But here's the issue. How confident are we that our statistical results are valid? Maybe we didn't check for outliers like this. And maybe, unfortunately, there are a few extremely expensive houses that are lying beyond the overall trend, like the red line. And if we include them, the model may be skewed, like the blue line. That is, violating statistical assumptions can easily easily undermine our analysis if we don't have enough instructional resources. And there are numerous textbooks and frameworks to explain assumptions. However, they are rarely integrated into the tools the analysts usually use. Analysts usually use data, SPS, and R, for example, because they provide really powerful analysis functions. However, they do not help with the whole procedures, and they do not help us to verify assumptions. Well, some research will try to provide some support for assumption checking, but they do not provide step-by-step support, and they don't address the assumption violation either. Besides, few tools are integrated with computing environments such as Jupyter Notebook, where analysts usually perform their analysis because of its flexibility. So in response to these problems, we introduced guided stats, an interactive system within Jupyter Notebook that support guided statistical analysis. Guided stats consist of statistical workflows representing maybe a statistical analysis such as linear regression, and it consists of guided steps, which is the subtask within analysis, like checking outliers in this picture. And for the workflows, it allows users to switch between the interface and code smoothly. That is, it is a portal to serve for the guided steps to be integrated into the notebook coding environment. And for the step, they offer 3 types of guidance to ensure usability through their unique explanations. So in this system, we can see that steps are the most important component within analysis. Like in the linear regression, there are steps such as selecting dependent variable, checking multilinearity. And we offer 3 main types of steps in our system design. The first one is the user input step. It sets the parameters, allow user to set parameters. For example, the user can set the median housing prices as the dependent variable. And that second one is the result presentation step. It presents the final result of the analysis. And for this case, it presents the coefficient of the prediction models and also provide R-squared score for any measure of goodness of fit. And more importantly, we have assumption checking step. It checks if the assumption for analysis hold. It's really crucial to ensure the validity of the stats models through its explanations, which I will introduce later. Speaking of explanation are offered for each step in guided stats. And the first type of explanation is objective, is for all of the steps, explain why the step is necessary for analysis and how it contributes to the overall validity of the analysis. And we have another kind of explanation that is also for every step. It's called statistical concept and interpretation, interpret some steps concept within the step, and they help us to interpret the result using templates and also the actual number calculated from the data set and the analysis function. And only for assumption checking step, it offers suggested actions, help user to find ways to fix assumption violations. One of this form is to preset the future step. Like here in t-test, we can just set the equivariance parameters as true for checking homogeneity of variance. And we can also generate code for user to transform or investigate data sets if we have, for example, like if we have some potential outlier columns, and we can investigate the distribution of it using the code generated below. And all of the steps are integrated into workflows. Each workflow represents a stats analysis, and workflows can handle the coding UI exchange in a lot of forms. One of these forms is to allow user to bring in transform data set if they are gaining some insight during analysis and want to use the transform data set for further step on. And guided stats workflow can do that. And we also support actual codes to replicate previous decision made entirely in the UI. So user can just use this code to replicate what they have done in our guided stats. And workflow also support iterative development. It automatically updates when previous steps are modified, so user can just adjust the parameters to find the optimal one, and without starting over to construct all of the steps again. So after all, in stats analysis, ensuring ability is very important, and guided stats do that by incorporating well-supported visualization and explanation and assumption checking. However, we don't support numerically untestable assumptions like identically independently distributed assumptions in linear regression. And maybe future work can try to add guidance on them by incorporating domain experts' knowledge, or maybe incorporate more consideration of the methodology or experiment method. And also, with the prevalence of LLM, maybe we can try to include LLM into our tools to support real-time Q&A for explanations, and maybe, or just alerting assumption violation is a new kind of form of code UI integration, and we're really excited about it. And that's all for my presentation. It's my first time to be on the HCCI conference. I'm really looking forward to hear from your feedbacks. Yeah, thanks.
Okay, great. Thanks, Yuqi. So we have one question on Slido that we can ask and take any follow-ups to Discord. Do you provide guidance on what types of tests might be appropriate? So like a t-test versus, say, an ANOVA.
Yeah, this is a very good question. So in terms of what type of tests will be appropriate, I guess it depends heavily on the experimental design and the kind of like analysis result the analysts really want to have. So currently we don't support that kind of test, but it will be because it includes more domain knowledge. But in the future work, we can definitely try to incorporate them by introducing more human UI collaborations, I guess. Yeah.
Okay, great. So I think that's good for this presentation. So very cool. Any follow-up questions, we can just take them to Discord. So let's go ahead and move to our next presentation. So Yunfei Liu will be presenting FCNR, fast compressive neural representation of visualization images.
Hi everyone, can you see my screen? Yeah, hi, I'm Yunfei from the University of Notre Dame, and I'm presenting our work FCNR for large-scale Sivas image compression. For time-varying dataset, given different visualization parameters, including viewpoints, timestamps, transfer function, and ISO value, a great many of Sivas images can be generated through direct volume rendering or surface rendering. They are significant for scientists to have a quick overview of the data and figure out the key features. However, there are many challenges limiting the transmission and storage of large volume of Sivas images, which calls for a more efficient compression method. Extensive research has been conducted in image and video compression. Implicit neural networks, as shown in Figure 1, represents complex data as continuous functions instead of discrete grid-based formats. INR enjoys widespread applications, especially in video compression, and has recently been extended to Sivas image compression by Nervi. On the other hand, stereo-based image compression, shown in the Figure 2, compresses images simultaneously in pairs to make use of their similarities. And what are stereo images? They can be simply interpreted as images taken from a slightly different viewpoints to simulate the perspective difference between the left and right eyes. As the example shows, they possess rich mutual information that can be made use of. When it comes to Sivas images, we can extend the concept of stereo images to images with close viewpoints. However, compared with stereo images, Sivas image compression is harder due to the complex transformations, such as the 3D rotation of the volume and the greater differences between close views and additional dimensions. In summary, Sivas image compression shares certain similarities with INR and stereo image-based compression, respectively, while also differ from them since Sivas images are more complicated in additional parameters and complex transforms, which makes the integration of parameters and mutual information among different views a necessity. Therefore, we present FCNR trying to take advantage of the features of both methods. Here is a quick overview of the method. FCNR consists of an encoder and a decoder. The encoder takes a pair of Sivas images with close views as the input and encodes them into compressed bit streams. After that, the decoder decodes the bit streams and reconstructs the original images. First comes the encoder. We improve the existing ECSIC method by introducing joint context modules, which can exploit mutual information between image pairs in a global manner, therefore allowing for more complex transformations. For the decoder part, we employ the stereo context module and model the latent representation by Laplacian distribution from time steps and viewing angles. We further condition the distributions of the right parameters from the left to reduce the bit rate. By combining the rate loss, which is aimed at increasing the compression ratio, and distortion loss to reduce the reconstruction error, we train the model on both direct volume rendering and isosurface rendering images from 3 datasets: the Vortex, Tangaroa, and Tornado dataset, and experiment details are shown. We compare FCR with 3 INR-based methods, eNerve, HNerve, and Nervi, and 1 stereo image-based baseline, ECSIC. Here is an overview of the results. From the image, we can see that FCNR reaches much better compression quality than INR-based methods. Though the visual quality of FCNR and ECSIC are similar, we can conclude from the figure that FCNR reaches higher PSNR in every epoch, and the table shows more quantitative results. We can see that our result, FCNR reaches much better results than IR-based methods in compression quality, and faster speeds in encoding and decoding. Moreover, it achieves better BPP than ECI-CIC in all cases. And here is a video showing the visual quality of FCNR more intuitively. Yeah, since FCNR is extended from ECI-SIC, we further conducted an ablation study to show the difference. The improved quality in lighting and edge proves the effectiveness of FCNR. And we can conclude that FCNR is prospective with much faster speed and quality than INR-based methods and better compression ratio than the ECI-SIC. However, it still lags behind INR in compression ratio. Our future work aims to address this and take more visualization parameters into account. And the research is supported by the following funding sources. And thank you very much.
Okay, thanks, Yunfei. We have one question in the Slido right now. How sensitive is the approach to highly dynamic data compared to more static ones in terms of reduction?
Yeah, well, since we take images as pairs as input, and we want to exploit the mutual information between the image pairs, therefore, the input images can be dynamic, but if the two input images are rather different, the result may be not as good as we expect.
Okay, and then one more question just came in. Nice work. Is the code available?
Yeah, it is available on GitHub, and you can check it on our paper.
Okay, yeah, and if you want, you can post a link to on Discord, Yunfei.
Okay, I will do that. Thank you.
Okay, great. So any follow-up questions, again, we can take those to Discord. Thanks, Yunfei. Let's go to our next presenter, Sneha Gathani. It will be presenting Groot, a system for editing and configuring automated data insights.
Hello, everyone. My name is Sneha Gathani. I'm a PhD candidate at the University of Maryland, and I'm excited to be presenting the Groot system developed for editing and configuring automated data insights. This work was done during my internship at Tableau Research in collaboration with Anna Kreisen, Vidya Satlur, and Arjun Srinivasan. Automated data insights are commonly seen in both commercial and research-focused visualization systems. These insights typically appear as textual statements alongside visualizations, as seen here, and aim to highlight key statistical data facts such as outliers, correlations, extreme values, differences, and distributions. While these insights support data exploration and chart interpretation, they operate as black boxes, providing users with only limited visibility into how the insights are generated, thereby reducing the overall usefulness of the insights. Insights in existing systems are generated using predefined underlying logic or heuristics and fixed templates. However, this often restricts the users from obtaining or extracting more meaningful and relevant information from the data and from the default insights generated from it. For example, current systems easily call out correlations between attributes, but fail to highlight when there is no correlation, like between sales and discount, as we see here. Similarly, extreme values like minimums and maximums across nominal categories like products may often be called out by systems, but more important insights such as significant differences may be overlooked by current systems. Even though users may want to add such additional insights, users cannot, since existing current automated systems offer no room for flexibility or customization. Like, for example, default insights generated by systems might flag a large number of data points as outliers, leaving the users with only the option of either accepting or rejecting these insights without really understanding how the system identified them as outliers in the first place. Such lack of flexibility or control over the insights generated further limits the usefulness of current insight generation process. To address these limitations, we developed the Groot system. Groot is an interactive system that empowers users to proactively specify and refine automated data insight engines in visualization tools. It provides greater transparency and control over the insight generation process by enabling users to edit, customize, and reconfigure the underlying heuristics and templates of default data insight. We designed Groot by conducting formative interviews with 6 users who actively designed or used automated data insights. From these interviews, we identified 4 key design requirements for Groot. First, Groot was developed to help users interpret system-generated insights by making the underlying heuristics more transparent. Second, Groot was implemented to provide the ability to reconfigure the system's default heuristics so that users can adjust how insights are generated. Third, Groot was designed to enable users to define custom insights as automated systems missed out domain-specific details. And last, Groot was equipped to ensure that insights dynamically updated based on changes made to the dataset. Now let me demonstrate Groot with a scenario of a business analyst exploring the Superstore dataset. The analyst looks at various attributes, and based on the type of data and based on the type of the data attributes, different charts and insights are generated. For example, exploring the sales and region.
Maybe we can skip and come back later.
Generated, and this calls out correlation insights. Similarly, exploring sales, regions, and product categories brings up stacked bar charts, emphasizing extreme values, as shown here. These examples reflect how current systems generate default insights using fixed heuristics and templates. Now, as the analyst explores and notices any null or unspecified values, they can delete them directly from the dataset, and this prompts Groot to automatically update the charts and insights as shown here. Continuing the exploration, the analyst looks at the sales by region bar chart and is curious about the differences between the regions. So Groot allows them to use direct manipulation to surface any additional insights based on this selection. So for example, selecting one bar chart shows its values, while selecting 2 bar charts shows also its difference, and selecting more than 2 bar charts reveals the sales order. The analyst, being interested in the sales difference between the central and the south regions, propagates this to the engine. And on propagation, Groot not only updates this current not only updates this insight into the current chart, but also adjusts the insight engine to highlight this difference by default for any future explorations that the user does, such as when they explore something like sales versus unit price, you can automatically see the difference between these regions. The analyst then explores whether increasing sales leads to higher profit and sees a strong correlation insight being seen here. Next, they want to see if the product-based margin impacts sales or if discounts may boost the sales. However, the system does not call out any of these insights, and this is likely because there is no explicit correlation detected between them. So to address this, Groot offers an interactive editing interface, allowing the analyst to customize the logic. They can, for example, select a highlighted range of values to highlight and also edit the template to call out the no correlation insights. On propagating this, the system calls out the no correlation between the discount and sales scatter plot, as well as the product-based margin and sales scatter plot that we observed before. So this way, Groot is able to help the analyst to tailor the default insights to their specific needs. The analyst now looks for, let's say the outliers between unit prices and notices that there are so many outliers being pointed out, even the ones with the lower price. So curious as to why this is happening, they might want to find the underlying formula for what this is. So GRUD allows them to view the formula and also adjust the threshold according to their domain expertise. And this refreshes the insights, and significantly lower number of outliers are being flagged now. So this shows how GRUD enables the analyst to reconfigure existing logistics and existing heuristics that are used by the system. Finally, GRUD allows the analyst to add custom insights. For example, if they want to find, say, the average, the percentage of shipping costs for a specific product category, they can define a parameterized template where they can add formulas and calculations are made on the fly. And all of these customizations are recorded in GRUD so that users can access these updated insights instead of going and looking at these default set of insights only. Looking ahead, we see an exciting opportunity to expand GRUD. One promising approach is to integrate LLMs, of course. Currently, GRUD relies on heuristics and templates for generating insights, but LLMs could enhance this process by improving how the insights are phrased, create more richer narratives, and related insights. Another opportunity lies in utilizing the metadata generated by GRUD to support other applications. So like, for example, you could use the data to support visualization search tools to deliver more domain-specific results. Additionally, the metadata could be used to propagate insights to other similar data sets, saving time to have users already reuse these tailored insights instead of having to start using a new data set from scratch and tailor it on their own. To summarize, we developed the GRUD system to empower users to interactively edit and reconfigure automated data insights, making the underlying working transparent to the users and enabling them to customize and tailor the default insights to the individual needs. Therefore, GRUD enhances the overall value and usability of automated insights. Thank you for listening, and I'll be happy to take questions.
Okay, great. Thanks, Sneha. So in the interest of, we're running a little borderline on time, I'm going to suggest if you have a question for Sneha, and actually one question I would like her to answer, let's take it to Discord and we can answer it there. And I want to know how you came up with the name GRUD. So we can take that and any follow-up questions to Discord.
Thank you.
Okay, so let's go ahead and just move on to our next presentation. This will be Charles Perrin will be presenting visualizations on smartwatches while running. It actually helps.
At least I'll try to convince you of it. Yes. All right. Hi, everyone. So this paper presents the research that Sarina conducted for her master's thesis with me and with the help of Wang. First of all, why is looking at smartwatches and running an interesting problem? There are two main reasons why we looked into this. Millions of runners use smartwatches to access data in the form of text while they're running. But here's a video of me running and talking out loud, which is a bit weird, but illustrates well our first motivation. Metrics like heart rate, speed, etc. And it's impossible to look at my watch, because if I do, I fall, and it has happened to me many times, so not sure how to do it, but I need something better than my watch. This first motivation is that accessing running data breaks the running flow, it's often ineffective, and it's possibly hazardous. Our second motivation is that running requires focus. And here is another video snippet that actually recorded during a race. For the past 5 minutes, I've been trying to make some calculations, and it's impossible. Even the simplest ones, just because my brain is always interrupted by where to put the feet or doing other stuff, and I was just trying to estimate the pace at which I should go overall to complete the race in 5 or in 6 hours. And it's so difficult. So this illustrates well how performing even the simplest data understanding task can be challenging when we run. And I don't know if you know runners, but we often say we don't have any brains and we can't do any math. And of course, being visualization researchers, we thought visualization should help, because we know that glanceable feedback on smartwatches can help track health or activity levels, that glanceable visualizations are useful on smartwatches, and also that visualizations can be useful when we run on a treadmill, so in an indoor low-risk environment. What we don't know, though, is the extent to which visualization is helpful in realistic running settings in which runners experience reduced cognition and must focus their attention on their environment, as I just showed you in those videos. So in this work, we contribute the first study on the usefulness of using visualization to perform realistic running tasks in a realistic running environment. But before this, we needed to know what data fields runners use when running. And so we combined an existing survey with our own survey and our own experience as runners as well to find that runners typically show 3 to 5 data fields on one data page on their watch, and that these are the 4 most needed running-specific data fields. We created 5 tasks for only 3 of these 4 data fields, given that 2 of them, elapsed time and distance, are very similar. These 5 tasks are realistic and meaningful to runners, and also of different types. They ask runners to estimate what proportion of a run they've completed, whether they are going too slow or too fast, and how much they need to adjust their speed, and whether their heart rate is within range and how much they need to adjust it. And you can read the paper for more details on this. The second step was to design data pages. We used a standard split screen layout like this one to show the 4 data fields. And we designed representations with text only and with visualizations. Elapsed time was always shown with text. The study didn't include tasks related to elapsed time. For pace, text shows current and target pace, and visualization is a dual bar chart with a baseline centered at the target pace, which is a gray vertical line. There's a small rectangle that shows the current pace. If it's on the left, you're too slow. If it's on the right, you're too fast. For distance, text shows the number of kilometers already run over the numbers of kilometers to run, and visualization is a progress bar that gets filled based on distance already run. For heart rate, text shows the current heart rate value and the target range, and visualization is a speedometer with 3 zones and an arrow that points at the current value. Green is good, yellow is too low, and red is too high. And we then created 2 data pages for the study. One that shows heart rate with text and pace and distance with visualization, and one that shows pace and distance with text and heart rate with visualization. Again, you can find details and rationale for all those design choices in the paper. For the study, we hypothesized that participants would be faster to complete all tasks with visualizations than with text only. We had 20 runners who completed 13 task instances while running with the first data page that showed a synthetic, realistic data set. Then they took a break, and then they did the same with the other data page. There were fossil Gen 6 smartwatch and wireless AirPods because they were running around a novel track, and they were asked questions verbally by the experimenter, and they also answered verbally. We analyzed completion times using confidence intervals. Basically, for each task, we show bootstrapped mean completion times with text in pink and with visualization in blue. And the difference between text and visualization is shown in gray. Here we have a large gray bar with a narrow confidence interval, so we can say with strong confidence that participants were much slower to complete the task with text than with visualization, with both statistical and practical significance. And we found this to be true for all tasks, with participants being between 1.6 and 7.9 times slower with text than with visualization. Subjective preferences yielded similar results. So here is a summary of participants' answers on Likert scales for text and visualization for each data field. Basically, green means good, orange means bad. And what we see is that runners largely preferred visualization to show distance. They thought visualization is clear, helpful for the task. They said they would use such visualization. The results are similar for heart rate, and for both data fields, they found that text was clear but not very helpful. For pace, the results are a bit different. They found text to be clearer, actually, but visualization to be more helpful. All right, so what did we learn here? Even with simple tasks that involve few numbers, visualization helped significantly. And we got confirmation that runners don't like to have to think about numbers. They told us things like, I don't like to do any sort of math or thinking, so something that shows me where I am and where I need to be is pretty handy. That being said, the need for visualization is both task dependent and context dependent, and sometimes numbers are more than enough. Most interestingly, running is a promising application area to study the role of visualization under limited attentional capacity. There is lots of data and tasks, lots of runners, lots of context, and runners really love technology. We also found through this research that as a field, we have little knowledge and history of conducting this kind of realistic studies, and there is a clear opportunity to develop new methodological frameworks there. So this is just the beginning. Come conduct visualization and HCI research about running with me in the VIXI lab at University of Victoria. Thank you.
Okay, great. Thanks, Charles. So in the interest of finishing on time, there's a couple questions on Slido. I think our tech will move those to Discord. We're going to go immediately into our last presentation. So micro visualizations on smartwatch, assessing reading performance while walking. So not running this time, walking, by Faru Griwe.
Yeah, thank you. So hi everyone. My name is Fairuz. I'm a PhD candidate at the Institute of Visualization and Interactive System at the University of Stuttgart. And I will present on behalf of my co-authors, Tanya Blaszek, Li Jiao, and Petra Eisenberg, our paper microvisualization on a smartwatch assessing reading performance while walking. So first, let me introduce what we refer to by microvisualization in our research context. So microvisualization are small-scale visualization of few square centimeters, typically the size of a smartwatch display. And even when prior research found that these glanceable visualization are more often used on the go, we still know little about how motion can affect reading performance when with these microvisualizations. So for this reason, in our paper, we investigate the influence of 3 walking trajectories and 3 walking speeds on the reading performance of microvisualization on a smartwatch, also on the mental and physical load of the task in general. So in the first study, we explored microvisualization reading performance under 3 walking trajectories, including a one-way simple line trajectory. In this condition, participants were asked to read the visualization from the smartwatch while walking between 2 known points and along a straight line. Then participant also had to walk along a circle trajectory, then also walk around 3 cones that we placed at the center of the study room, creating an infinity-like trajectory. So for the 2 latter conditions, participants were walking continuously, and they were notified with a vibration from the smartwatch to visualize the visualization. In the second study, we explored microvisualization reading with 3 walking speeds, and to control the walking speed, we used a treadmill. So we operated the treadmill at speed of 2 km per hour for the slow walking phase, 4 km per hour for the fast walking phase, and we asked participants to start stroke at the 6 km per hour speed, which was the fastest. Also, we included 2 sedentary conditions as baseline, including sitting on a chair and standing. So while performing the walking and the sedentary conditions, we showed participant night watch face stimuli with common smartwatch microvisualizations, including daytime, weather information, and also a set of 4 complications showing progress chart of fitness data. We asked participants to focus on the 3 radar charts and to indicate in the first place the data type with the highest progress, then to estimate its progress in percentage. For example, here you can see that the calorie burned has the highest progress with 75%. We also set all proportion percentage to be multiple of 5 and set a difference of 5 and 10% between the highest progress chart and the 2 other proportions. Coming to the results. So we annotated the time participants took to verbalize their responses, starting from the moment their arms were in a stable reading position. For the 3 walking trajectories, the mean response time was on average 5.6 seconds, and we did not find any evidence of difference between the 3 conditions. In contrast, response times were way shorter for the 3 walking speeds and the sedentary conditions, on average 2 seconds. And the highest response times were during the slow walking pace condition, while the shortest response time were during the 6 km/h jogging condition. For both study, participants were very accurate in finding the data type with the highest proportion, with an average of 95% for the 3 walking trajectories and the 3 walking speeds, and up to 98% for the standing condition. And also our results showed evidence of difference between the standing condition and the 6 km/h condition, as well as the 2 km/h condition. However, when estimating the proportion, participant answers were less accurate, with an average of 72% for the 3 walking trajectories, 78% for the 3 walking speeds, and similarly to prior results, participants were more error-prone with the 6 km/h speed condition, and their reading performance was the best while standing. Participants also did not find the overall task difficult, in particular with the sedentary conditions, and rated the task to be more challenging with high speeds and with trajectories that contained obstacles. Also, they were in general quite confident about their answers, even though we can see that with the 6 km/h condition, their confidence was slightly lower compared to the other condition in the second study. Participants rated performing the reading task with the 3 walking trajectories to be more mentally demanding compared to the sedentary and the 3 walking speed conditions. And according here to participant feedback, they mentioned that coordinating between walking, reading the visualization, and also following a specific navigation task path was mentally demanding to some extent. In contrast, the high-speed walking condition was perceived as the most physically demanding among all the conditions. So some participants in the first study mentioned that they don't see themselves reading data at a detailed level, especially while in motion. For this reason, in the second study, we asked participants who reported owning or using smartwatch about their preferences for reading overview or detailed information on their smartwatches, and we found that among the 27 gathered answers, 17 preferred reading overviews and 10 were more for checking details. So this somehow leads us to mention that smartwatches should show information at a holistic and also detailed scale simultaneously or on demand if necessary. As a conclusion, through our 2 studies, we found that participants can read data relatively accurately while walking different trajectories and different speeds. However, the reading performance can be negatively impacted when reading data at a detailed level, but also under high walking pace. In our case, it was 6 km/h speed, and in addition to coordinating it with another task, for example, the navigation task. And at the end, also, we encourage future studies investigating microvisualization reading in motion to experiment with broader range of walking speeds and also walking trajectories, including outdoor scenarios, and also to explore different activities. With this, I come to the end of my presentation. Thank you for your attention.
Okay, great. Thank you, Farouz. So we're actually at the end of this is the time now that the session is supposed to end. So if you have any questions for our last speaker, feel free to post those on Discord. We can just all transition over here and have that discussion. So I want to say thank you to all of our presenters in this session and everyone watching. I hope you enjoyed the presentations. And yeah, have a good Wednesday, finishing up VIS, and a good rest of the week.
Thank you.
And thank you for moderating.
Thank you.
All right, thanks everyone.